Okay, the local min is the same basic thing. You just got to replace a few symbols, right? So if C is on an interval, C is in an is in an interval I over which f of x is defined as f of x, if f of c is less than or equal to f of x for all x in any open interval containing C, then fc is a local min, and C is the location of local min. All you gotta do is change max to mins and change this inequality. Okay? And that's the definition for local min. Alright? So now I just want to draw a picture for these. Try to explain why it has to do with open intervals and what this definition is really trying to get at. Okay, we'll start with a picture like this. Hold this A, hold this B here. That'll be good enough for us. All right. First, let's talk about the global or absolute maximum. Does this picture have an absolute maximum? According to the picture, is there an absolute maximum? Let me draw this a little bit better. This guy. He's just trucking up there. This one's really, this one's going down forever. This is a little polynomial. This is the important feature of our polynomial. This is the end behavior, and that's the end behavior in that direction. Is there an absolute maximum?
Nope.
No, why not?
Because it keeps going up.
It keeps going higher forever, right? There's no highest value this function ever takes on.
Yep.
As soon as you claim that one point is possibly a global maximum, I'll find you one that's higher, right? Is there a global minimum? Is there an absolute min?
No.
Nope, same reason. As soon as you claim that, say, I don't know, right about there, that's the lowest value it takes on. I'll show you one that's lower, that one, and I'll show you one that's even lower, that one, and so on and so forth. So there's no, can't use it. It's not a number, so you cannot use it. That is correct. All right, is there a local max?
Yeah.
At what location is the local max?
A.
X equals A, very good. All right, so what this is trying to say is if you can create an open interval, right, that contains A, and that maps up to here, right? That would map up to here. So all of the f of x's that are sitting around this location, right? If they are if they're all smaller than f of a, which in this case they are, right? Every little f of x crowding around f of a is just slightly below it in height, correct? So f of a ends up being the peak of this little mound in a sense. That's what it's trying to say, all right? So now you also have a local min according to the definition. I could create some open interval where this would be the lowest point on that interval. So that's going to be your local min. Okay? All right, now we're going to change the picture a little bit. So I've truncated a little polynomial here, and now it has a restricted domain. Now I want to ask the exact same questions. Does this have an absolute maximum now?
At C. Yeah.
Hold on a second. Hold on a second. C some sentence in C, so I'll make him somewhat correct you. I'll write a C there. Right?
Yeah.
Over here, I'll write a D. Is that okay?
Yeah.
Just when we talk about those locations. All right. So is there an absolute maximum at C?
No.
No.
There is not. Why not?
Because this is whole open.
Because what?
It's a whole.
It's a whole. There's no function there.
It's a whole.
All right. No function there. So what about right before C?
Yeah.
Yeah.
What about the little dot right before C?
Yeah.
Yeah, we don't know that.
As long as it doesn't continue that way.
Yeah.
So here's the subtlety of it. Is there a particular dot right before the C location?
No.
Yeah.
No.
No.
You can always get closer and closer and closer to what would have been f of c. You can always get closer and closer and closer to this height, right?
Mhm.
So as this function moves up here to this hole, it's getting higher and higher and higher forever, right? It's certainly heading towards a fixed value, but it's always growing. It never stops at some little point right before C to claim that would be the highest location, right? So does that make this the absolute maximum?
Yes.
Since this is not, does that make this one the absolute maximum?
Yeah.
The answer is no, because this location here is still higher than that one. So that can't be the absolute max, so I can find things higher. I just can't, it doesn't have one. I just can't find the highest one. There is no highest one. It keeps getting higher and higher and higher. Not in the usual sense of approaching infinity, but it's certainly getting higher and higher and higher, approaching this number here, whatever it happens to be. Does that make any sense? Okay. What about an absolute min? Does it have an absolute min? It does, because that's a filled-in dot, so it reaches that point, right? Whatever f of d is, f of d is smaller than every single f of x value in this picture, right? So that is certainly going to be its absolute minimum. So now I got another question. Now that this is an absolute minimum, is it also a local minimum?
Yes.
It is.
Let me ask you a simpler question. I'll draw a different picture. Actually, a simpler question first. Hold on.
What was the question?
I forgot. But I'll remember it in a second. Okay. So there's our standard parabola x squared, right? Does that have a local minimum?
That has an absolute.
What's that?
I mean, it has an absolute.
Does it have a local? According to the definition of local minimum, does it have a local minimum?
No.
Yes. I can draw a little open interval there, and this is the smallest value in that little open interval, right? That's all it takes, right? So it has a local min, and that local min is also the absolute min, okay? So there are plenty of cases where the absolute max of min is also a local max or min, right? A vast number of cases.
Wait, say it again. You said what?
There are plenty of cases when you're graphing where the absolute minimum or maximum is certainly still a local minimum or maximum according to the definition.
Okay.
So when you're answering questions, especially online, you should not discount, you shouldn't say, well, it's absolute, so therefore it's not part of the local grouping. You know what I'm saying? It's also going to be a local in many cases. All right?
So are these like mainly on curves, or they can just give you like a slanted line segment?
They give you anything you want, yeah. They give you piecewise
So it's
holes
not-
and dots and, yeah. That's why I'm drawing this little picture here, because you're going to have cases like this, they're going to try to trick you, right?
Now I'm saying, would they give us like something apart on the curve? Like say this is the interval. It's not necessarily like the curve when it changes directions.
Yeah, that's possible. Yeah.
Could you give us one example where absolute minimum is not local?
That's what I'm doing right now. I'm trying to get to this one. That's right. So now, we already established this is certainly the absolute minimum of this function, right? The way I've drawn it. So now my question is it also a local minimum? To be a local minimum, I have to be able to create an open interval around that location, right? Over which the function is defined. But I can't do that. As soon as I create any open interval around D, what happens? It's not defined on this side of D. You know what I'm saying? I can't create an open interval that contains D and that contains the function as well. Right? Does that make sense? This portion over here, all that, is not part of domain F, the way I've drawn the picture.
Yep.
So I cannot create an open interval in the domain of the function that contains this location. As soon as I try